Hi, welcome to this class. Today we are going to deal with floating points. We're going to talk about floating point instruction. So in MIPS, floating point operations are usually handled by coprocessor 1. When you want to write instruction in a single precision, which we'll cover, you do add.s or sub.s, anything.s. And when you want to do in double precision, you do .d. And for comparison, you do c.x.s. The x can be equal to, less than, or any other thing, which we'll cover. So these are some of the formats that this is the instruction formats that is used: 6 bits opcode, 5 bits format. We have the target, source, destination, specific floating point operation, and COP, which literally says tell the hardware to use coprocessor. Let's talk about a few examples. So when we are doing single precision, addition, you just do, instead of add, then you bring your 3 registers, you're going to do add, then add.s, then three registers. Same with sub, same with multiplication and division. For floating point, you're going to do the same with d. The difference between the floating point and the single point and the single precision, and the double precision is that in the single precision you can add two things like this and store it in the next register without considering the fact that it can be over 32 bits, right? So for example, when I added f4 and f5 in this example, I store the answer in f3. But if I was doing double precision, when I add f4 and f6, I'll store it in f2. And the reason is that f2 is only 32 bits, but the answer may be 64 bits because it's double precision. So we're going to use f2 and f3. So in double precision, you only use evenly spaced registers. Like f2, you cannot use f2, then you do f3, f4, because the answer may not fit into just f2. So when you use f2, you need to leave f3, then you do f4 and f6, knowing that f4 may occupy f4 and f5, and f6 may occupy f6 and f7. Same with all the other instructions. Now for our data transfer, instead of load word, we do load word C1, and for double, we do load double C1. So for load word, C1 is like the normal load word, but then load double C1 is going to load whatever answer into F2 and F3, right? Same similar intuition for the store. And in comparison to, you use the X as your condition. So you see, compare, when you're comparing, set C equals 1 if X equals, if S is equal to something, right? So for example is C equals 1 if F1 is less than or equal to F2, and this LE is the less than or equal to, and this is in single precision. If we're doing double, this would have been double, so it could have been C equals 1 if F1, let's say F2 is less than F4, right? Less than, then we do double. So this is a double and this is a single precision. I'll go through example problems so we understand. Now let's talk about floating point multiplication. This is the algorithm to go through floating point multiplication. To better explain the algorithm, I'm going to just use any example. Actually, let's go with the example that's on this slide. Before we go ahead, we need to understand all the points of a floating point number. So let's say this number, which is negative 6.5. When we tell you to write this in binary, the first bit is 32 bits. It's divided into, the first one is a signed bit, the second 8, I believe, 1 2 3 4 5 6 7 8. The second 8 is going to be the exponent, and the remaining is going to be the mantissa, because this is a single precision. If it was double precision, the first was going to be the sign bit with a 1 or 0. The next 11 will be the exponent, and the remaining whatever number is left, 52 bits, will be the mantissa. So for example, in this example, if we need to convert negative 6.5 into a single precision decimal representation, we know that is a negative number, so whatever happens, our first bit is 1. Now the next thing we're going to do is that we're going to convert 6 into binary, and we will convert 0.5 into binary. To convert 6 into binary, we already know it's 110. To convert 0.5 into binary, this is what you're going to do. You're going to take 0.5, you multiply it by 2. The answer you got is 1.0. It's 1.0, and you take this 1 as part of your answer, and we're going to continue, but this is 0. If we multiply it by 0, it's still going to give us 0. So the answer to negative 6.5 in decimal is literally going to be negative 110.1 base 2. Right? So to write this, we know that our sign is negative number, and now we need to determine what our exponent is. So our exponent is going to be, we have what we call the bias. Because it's a single precision, the bias is 127. If it was double precision, the bias will be 1023. So to get the bias, you're going to just add 2 from, no, sorry. This one, when you convert the negative 6.5 to binary, we drop the negative, so it was 110.1 base 2. We need to normalize it. We need to put it into the normal form, which is 1 point something, right? So here, sorry, so this one is going to be 1.101 times 2 to the power 2, because we did 1, 2, we moved 2, right? So now this is the normalized form of negative 6.5 in decimal, and in binary, sorry. And to find the exponent, because this is a single precision, you're going to add 127 to the number that 2 is raised to. So you're going to multiply it here. You're going to add it here. Sorry. So when you add this, you're going to get 129, which is what we found here. So our exponent is 129, and we know the exponent should be 8 bits. So what you're going to do is that you're going to write your your sign here, then you're going to write the exponent 100 0001 1 2 3 4 5 6 7. I think I need one more 0. So yeah, this is our sign, this is our exponent. Now the remaining is a mantissa. The mantissa is anything after the decimal, after the point, right? After the point. So it's 10101, then we stuff it with zeros, enough zeros to make it up to 32 bits. So that is how floating point is, and that's how you convert it into single precision binary. If we're doing double precision, the difference is that this 1023 would have been added to 2 instead of that 127, and this mantissa will be 52 bits. All right. Let's do another example. So it says that convert this negative 2.5 into a single precision and double precision. I think it's a good example that we can start trying. Okay, so we know that I'm going to drop the negative, right? So 2.5 is 2 plus 0.5. And 2, when you convert it into binary, is 10. Is 0.45. To convert 0.45 into binary, this is what you do. You're going to multiply 0.45 by 2. The answer you're going to get is 0.9. So now you're going to take the 9, which is after the point, and you multiply it by 2. You can get 1.8. So as part of your answer, you're going to choose 0, you're going to choose 1. Now you're going to multiply 8 by 2, which is going to be 1.6, right? This is part of your answer. Now we're going to multiply the 0.6 by 2, which is going to give us 1.2. This is part of our answer now. I'm going to multiply 0.2 by 2, which is going to give me 0.4. This is part of my answer now. So now remember the answer I'm getting is 0.1110. Now 0.4 times 2 is 0.8. So this is part of my answer. 0.8 times 2 is 1.6. So this is part of my answer. 0.6 times 2 is 1.2. This is part of my answer. There's something that I've realized that some of you may not have realized. So from here to here, I think it's repeating. This part is repeating here. So I don't need to keep on going, right? So after I get here, I can stop and write a bar or something that shows that it is repeating, right? So the 0.4 in 0.45 in binary is 01110, but it keeps repeating. So this keeps repeating. You can write a bar or you can write it below. Now to put it together, negative 2.45 is literally negative 2.45, and this is repeating, right? So now what we need to do is that we need to normalize this one. To normalize it means we need it in 1 point something, right? So the normalization is going to be negative 1.001110, and this is repeating, times 2 to the power 1, right? So now that we have this, let's write it in single precision. I think okay, yeah, to write it in single precision, we already have converted it into our normalize. Now we know that it's a negative number, so the sign is 1, and the exponent is the bias exponent that we are going to deal with, which I already introduced us to. Is going to be the unbiased plus the unbiased exponent plus the bias. So right now, because we are doing single precision, we know that our bias is 127 here. Our bias is 127 because it's single precision, and our unbiased exponent is 1, and which is from here, right? So when we add both this one and 127, the answer is, so the answer here is 127 plus 1, which is 128. And when we convert 128 into binary, you get 1 0 0 0 0 0 0, right? So now let's go back to writing the whole thing. Our mantissa, as we know, is this part of our code. So it starts from the 0 0 1 1 1 0 0, and we know that this part keeps on repeating. So I'm going to go 1 1 1 0 0. You're going to do that until you get your 52 bits. No, sorry, this is the 32 bit one. So until you get the 23 bits that you need, right? So now putting everything together, we know the number is a negative number, so the sign bit is 1, and our exponent, our bias exponent, is 128 in binary, which is 1 0 0 0 0 0 0. Yes, and our mantissa is taken from here, which is 0 0 1 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0. So this is how you convert into single precision from any given number. Now, what about double precision? For double precision, something similar. Our sign is still 1 because the number is negative, and our biased exponent is the unbiased exponent plus bias. Now, when you think about it, our bias is not 127 anymore. It's going to be 1023 because it's double precision. When we add both of them, it's going to give us 124. It's 1, so it's going to be 1 plus, no, it's going to be 1023 plus 1, which is 1024. And 1024, when you write it in binary, as this, right? It gives you 11 bits. So at the end, the double precision, we're going to get the sign is 1, and this part is going to be our exponent, and the mantissa is this one, but we have 52 bits of them, right? So that's how we go about our double precision. All right, let's talk about floating point addition. So the next thing is that we've been given these numbers: 0xbfe 00000 minus 0xc06 00000. So now you need to convert to normalized binary. I believe you should be able to convert from the hexadecimal to the binary. And since the first number is 1, we know that it's a negative number. And before we tell you, we usually let you know that this is single precision or double precision. So this one is actually single precision. I don't think we mentioned it, but yeah, it's single precision. So what you're going to do is that you need to find your unbiased exponent. Remember, your unbiased exponent, your bias exponent was your unbiased exponent plus the bias, which is 127. So if you just need your unbiased exponent, you just subtract 127 from your bias exponent. So this part all the way to here, I believe this is 1 2 3 4 5 6 7 8 is your exponent. So when you subtract 127 from it, you get your unbiased exponent. In this case, this value converts to 127. So when you do 127 minus 127, you get 0. Now after you're done, everything else that is left, which is from here, is your mantissa, right? So that's how you do it. And for the other one, you follow a similar trajectory for the second one. And after that, what you're going to do is that you're going to put them together and you write it in your normalized form, right? So when you write it in your normalized form, the next thing you're going to do is that you're going to match the exponents. So you're going to take the one that has a smaller exponent, which in this case is the first one. Then you're going to change it in a way that the exponents match. So it was negative 1.11 times 2 to the 0. What we have to do is just move this floating point to the front so that we get negative 0.111 times 2 to the 1. When we get 2 to the 1, it now matches the second part. Now that the exponents match and we are working in the same base, you can literally just do your operation. So right now we wanted to subtract. Subtraction is the same as addition. You already know that. So it's the first one, which is negative 0.111 minus the second one, which is negative 1.11. You can add a 0. So this turns into addition, and the answer now is 0.111, right? So now that you have this answer, it's still times 2 to the power 1. But before you go, you need to normalize this answer. When you normalize it, you're gonna move this floating point here. So you're gonna get 1.11 times 2 to the power 0. Yes, times 2 to the power 0. So now you need to check whether it's an overflow or not. To check whether there's an overflow, you check the exponent. If the exponent is within your expected range, then it's not an overflow. For single precision, the exponent can be from negative 126 to positive 127. So there's no overflow. And right now that you're done with everything, all you need to do is to put the results back in your register and you will be good. All right, good. Now let's do our floating point multiplication. It's very similar. So here we have 1.5 to the base 10 times negative 0.4375 to the base 10, and we want you to work in floating point and work in binary. So what you're going to do is that you're going to convert this to binary. You convert this to binary. You already know that 1 in binary is 1, and 0.5 in binary from our previous example is 1. If you don't remember how it was done, you just take the 0.5 and multiply it by 2, we got 1.0. So 1 is part of our answer, and if we continue and do 0 times 0, it's still 0, so we don't need to continue doing it. So now the answer is 1.1 times 2 to the power 0. For negative 0.4375, to convert it, I've written it here, but I'm going to write it down here. To convert it, you just multiply the 0.4375 by 2. The answer is 0.8750. So we know that 0 is part of our answer. Now we're going to multiply the 0.8750. We get 1.750, which means 1 is part of our answer. Now we're going to multiply the 750 by 2, and we get 1.50. We know that 1 is part of our next answer. We multiply the 0.5 by 2, we get 1.0, and we know that this 1 is part of our answers. So now we know that our answer for the floating point is going to be the first part, which is the negative part here. So it's going to be negative 0 point, whatever we got at the bottom here, which is 0, 1, 1, 0. And when we are done, we need to normalize it. So we move the point here twice. So it's going to be 1 point negative, sorry. How do I delete this? Okay, it's going to be negative 1.11 times 2 to the power negative 2. And now what we are going to do is that we are going to add the unbiased exponents of both. One is negative 2 and one is 0, so when we add it, we get negative 2. And after that, we can just multiply the significance. When we multiply 1.1 by 1.11, you can excuse the negative sign, because there's a way to know what the sign is eventually going to be. So when we multiply 1.1 by 1.11, what you can do is that you can drop every decimal place, but you know that we have 1, 2, 3 decimal places in the product. So after you do your multiplication, you just start from the bottom, from the back, 1, 2, 3, then you put your decimal, not your decimal, sorry, your floating point there. Now that you're done, you know the next thing, right? You know that you need to convert it to normalized. So this is going to be, instead of 0.101, it's going to be 1.0101 times 2 to the power negative 1. And now you know that the answer is negative is because it's negative 1 is a negative times a positive. The answer is always negative. If you want a formalized one, you can always XOR the signs, and you know the answer. If they are both negative, the answer should be positive. If they are both positive, the answer should be positive. If one is negative and one is positive, the answer should be negative. So literally you get to get this part out. All right, let's talk about integers, integer multiplication. Now we're still dealing with binary, but we are moving from floating point to this one. Let's take a typical example from my work here. Negative 6 times 5. Negative 6 in binary, not negative 6. Negative 6 in binary is actually 110, right? 0, 1, 1, 0. But when we do 2's complement, it's going to be, for 2's complement, we need to flip all the bits, which is going to give us 0, 1, 0, 1. Then we need to add 1. It's going to be 1 plus 1 is 0, 1. The 1, 1, then 1. So negative 6 eventually is going to give us this one, 0, 1, 1, 0, right? As we just got here. So to do this algorithm, what you do is that the first part, when you're multiplying A by B, A is your multiplicand and B is your multiplier. So you draw a table, and in the first part you have your multiplier, which is the second part, and in this case it's 5. And the second part is your multiplicand, which was 0, 1, 1, 0. But in the multiplicand, you need to stuff it with enough zeros so that it can be, the bits will be twice what you have. Mind you, this is usually a 32-bit operation, but to make it easy and simple, we are using just 4 bits. So if this was 32-bit operation, the multiplicand would have been 64. But because we are doing only 4 bits, the multiplicand became 8 bits. And the product is 8 bits. You know this from the fact that when you do mult in MIPS, you have to do mult, then 2 registers, then you realize that we have a low and high because there's a tendency that the answer will be more than the 32 bits, right? That's why we need to create space for double of what we need. Now here is the algorithm. Whatever you do, you're going to consider the last bit, the least significant bit of your multiplier. Well, first of all, when I start, I have a 0th iteration. 0th iteration is really not part of the iterations, just setting things up so that you can keep going. So I'm going to take the last bit of my multiplier. If the least significant bit or the last bit is 1, what I'm going to do is that I'm going to add my multiplicand and my multiplier. So that's what I did. I added my multiplicand and my multiplier, and I put the answer in as a product. No, sorry. I'm sorry. That's not what I meant. I'm going to add my multiplicand and my product. My multiplicand and my product. And I put the answer in my product. So my product has been updated. That is if the last bit of my multiplier is 1. And after that, I'm going to shift my multiplier to the right. And I'm going to shift my multiplicand to the left. Right? So when you see here, I shifted this one. I shifted it to the right. So it became 0, 0, 1, 0. And I shifted this to the left. It became 0, 0, 0, 0, 1, 1, 0, 0. Now I wrote it here, I wrote it here, I wrote it here. Cool. The next thing we are going to do is check that in the next iteration, we're going to do the same thing. We're going to check the least significant bit, which in this case is 0. If it is 0, you don't update your product. You're just going to copy your current product here. You're going to shift your multiplicand to the left, and you shift your multiplier to the right. So now we have 0, 0, 0, 1. And here, since we shifted to the left, we have 0, 0, 1, 1, 0, 0. Again, what is the value of our least significant bit? It is 1. Since it is 1, what are we going to do? We're going to add our multiplicand and our product. When we add them, we write the answer down. Then we shift our multiplicand to the left. We shift our multiplier to the right. We do that. The shifting, we do that for everything that you go through. So now, when I shift this to the right, it's going to be 0, 0, 0, 0, which is down here. When I shift this to the left, it's going to be 0, 0, 1, 1, 0, 0, 0, which is written down here. Now, in my 4th iteration, I'm going to do the same. I'm going to check the least significant bit. It is 0. So what I'm going to do, I'm just going to go and copy the current product as my next product. I'm still going to shift this, which is still 0, 0, 0. I'm going to shift this, which is 0, 1, 1, 0, 0, 0, 0, 0. Right? Now I'm going to write it here, and I'm going to write it here. Right? So when I get here, I stop. How do I know when to stop? So you're going to go through the iteration 32 times, if it is a 32-bit register. You're going to go through it 10 times. This is if you're only dealing with 10 bits. Now, since we're dealing with only 4 bits, we went through it 4 times, right? So this is our answer, but we are not done. Remember that the question was -6 times 5. So when we are done with this, we know that the answer should be a negative number, right? So we are going to negate this number. And how do we negate it? We're going to do the 2's complement, which means we're going to flip every bit 1, 1, 1, 0, 0, 0, 0, 1. Then we're going to add 1 to it. 1 plus 1 is 1, 0, so 0 remainder 1, 0 remainder 1. So we're going to put the 1 here. Now 0, 0, 0, 1, 1, 1. So that's how we got this answer. And this is the multiplication algorithm. right? We are going to do another algorithm, which is the division, integer division. For the integer division, when we start, there are a few things that you need to know. The quotient, is the answer that you will get. The more sorry, the quotient is the answer that you get. The divisor is the one that's going to divide, and the remainder is the remainder. In this case, the modulo. So you write this table, and again, the 0th iteration is always just setting up. When you look at this algorithm, it says repeat 33 times if it is a 32-bit register. So if it's a 4-bit number, 4-bit binary, we're going to repeat 5 times instead of 4 times, right? So you get it. So when you start, your quotient is 0. Your divisor is going to be your divisor is, if we have A divided by B, B is your divisor. So you're going to write your divisor. And this is the difference between here and the multiplication. See, in the multiplication, we start some zeros before it, but in the divisor, we're going to start the zeros after it, right? Now, your remainder is your dividend. Is that so? When you have A divided by B, B is your divisor, A is your dividend. And in the algorithm, what you're going to do is that whatever A is, you're going to put it as your remainder. And you're going to put zeros in front of it to make it up to times 2 of the register space. So now, what we're going to do from the algorithm, it says that check between the divisor and the remainder. Then you check which one is bigger, right? You check which one is bigger. If the remainder is bigger than the divisor, there's something you need to do. If the divisor is also bigger than the remainder, there's something else you need to do. So let's go with the first thing that is happening here. The divisor, in this case, is a bigger number than the dividend. Than the remainder. So what are we going to do? We're just going to copy the current remainder down there, right? And we are going to shift the divisor to the right. We're going to shift the quotient to the left, right? So when we shift this divisor here to the right, it's going to push 1 0 out, and it's going to put a 0 in front of it. That's how come we got this number. Now we're going to go through the next iteration. We're going to check, is divisor greater than the remainder? If it is true, just copy the remainder down. And again, shift the divisor to the right and shift the remainder, the quotient to the left. So when you shift the quotient to the left, you get this. When you shift the divisor to the right, it's going to put 1 0 here, and it's going to take this 0 here, and it's going to give you this number, right? We're going to go through. Again, we will shift here, this one to the right, this one to the left. Now we keep on shifting until something changed. So we are going to keep on copying it and shifting. So we're going to get to a place that is interesting. For example, when we get here, something changes. Now our divisor is not bigger than our remainder anymore. As soon as this happens, you go to your other logic. When this happens, you are going to subtract. You're going to do R minus D. So in this case, you're going to do R minus D, which is R minus D, which is 0 0 0 0 0 1 0 1. When you do this subtraction, this is literally 6 minus 5, you get 1 0 0 0 0 0 0, right? So you only do this if your remainder is bigger than your divisor. So now this is the new number you got, so you copy it down here. That's why we have it here. You're still going to shift this to the right, So you're going to get 0, 0, 0, 0, 0, 0, 1, 0. You're going to shift this to the left, but the difference here is that you're going to shift to the left with a 1 instead of 0. So instead of pushing a 0 here, this is what you're going to do. You're going to put 1, 0, 0, 0. You're shifting to the left and you're changing the least significant bit to 1, right? So for example, if this number was, let's say, 0, 1, 0, 1, you're still going to shift to the left, which is going to give you 0, 1, 0, 0. Then you change this to 1. So it's going to give you 0, 1, 0, 1. No, sorry. When you shift it to the left, when I shift it to the left, I'm going to get 1, 0, 1, 0. Yes. Then I change this, so it becomes 1, 0, 1, 1. Right? Cool. So now that we have this, and we have this answer, this is our answers that we're looking for, but we are not quite done. Just like multiplication, we need to figure out what the signs should be. For the quotient is always XOR of the operand. So if they are the same, what's the name? They're both positive, the quotient should be positive. If they are both negative, the quotient should be negative. But if one is positive and the other is negative, the quotient should be negative, right? So that's why the answer is, although the answer we got is 0, 0, 1, we need to negate it. And negating it, we do the 2's complement, which is 0, 0, 0, 1. You flip everything, so you're going to get 1, 1, 1, 0. Then you add 1. The answer is 1, 1, 1, 1. That's why this is the quotient that we got. And for the remainder, the remainder is always the sign of the dividend. So in this case, it was negative 6 divided by 5, and the dividend is negative 6. The sign is negative. So that means that the remainder should also be negative. That's how we got this answer. All right. So this is the few things that I wanted us to go through. And if you have a question, you can send me an email, or you can leave a comment under the video, and I'll try to answer it for you. Thank you very much.